redox reaction we can break down into different approaches here. Our book, the book has single replacement. Actually, there's one more. There's a combination, element plus element combination. Oh, this must be an old slide. Element plus element combination, single replacement, combustion, chart method, and then 4 and 5 we're going to skip. Potential diagrams and skeleton. Actually, 5 we're not going to skip. 4 we're going to skip. Potential diagrams. 5 we're actually going to do here. So one of them is missing in this approach. And so let me talk about the reactions first. So we'll just call it I. And that's going to be element plus element, what we call combination slash, the reverse would be decomposition. So element plus element combination, sometimes we have some choices, sometimes we don't. So for example, if we were to take some magnesium metal, did you know magnesium metal, does it burn? Yeah, magnesium metal actually burns. I think, do I have some here? Other metals oxidize. And so, in other words, burning is just this rapid oxidation process. And so if we burn it in O2, or oxidize it in O2, what forms? Is it MgO2 or MgO?
MgO.
It's MgO because magnesium is a fixed charge. It's always going to be +2. Therefore, we're going to have to balance this. O2 is a gas, so we need to write that. What do you think MgO is? Solid, liquid, gas, or AQ? Well, there's no water present in this one. So if there's no water present, then all the salts will be solid. And although oxides, you didn't learn the rules for oxides. Oxides are pretty soluble or insoluble. Like, for example, rust. Is rust pretty soluble? Insoluble. Or pennies. Pennies become oxidized. Can you wash the oxidation off pennies? No. And so these are solids. MgO is also a solid here. But this equation is not balanced. How do we balance it? We could either put a 1/2 in front of the O2, or we can put a 2 here and a 2 here. Either way. And then it's balanced. Now the reverse reaction is decomposition. So if we take some MgO, solid, then we might try to decompose that into the elements. Magnesium, solid, plus O2, gas. Again, we'd have to balance this, so we'll put in 2 MgOs and 2 magnesiums here. So this is the combination. This is the decomposition. Now sometimes what happens is multiple products can form. And so we got to figure out which forms. And so let's take a look at an example of that here. An example of multiple products forming would be like copper. Solid, because copper is a variable charge ion. And so one of the things that can happen is if you have your penny, initially when it starts becoming oxidized, you know what color it is? It starts becoming oxidized. Okay, that's a different type of, it can turn green, that's due to sulfur, sulfides. It starts to turn brown, right, or kind of orange, although copper is orange color, it becomes red-orange, something like that. Well, that turns out to be copper 1 oxide. What is copper 1 oxide? Cu2O, solid. This is copper 1 oxide. And so when your pennies initially become oxidized, they'll have copper 1 oxide, which has a distinct color that's different than this. What can happen is the copper 1 oxide can be further oxidized. And so we have copper 1 oxide becomes further oxidized to form copper 2 oxide. And what's the formula for copper 2 oxide? CuO, solid. That's copper 2 oxide. And so overall, what happens here is, let's balance this. What do we need to balance this one here?
2 oxygen. I'm sorry, 2 copper.
2 copper, 1/2 O2, and that should be good. So if we do 2 1/2, that's balanced. Or we can multiply by 2. That would mean 4 coppers, 1 O2, and 2 Cu2Os. We can do that as well. And the same thing here. How should we balance this? We're going to need 2 CuOs. Balance that. And then we're going to need 1/2 an O2 to balance that. And so the overall reaction is, this is black. And so eventually your pennies will turn black with the coating in copper 2 oxide. This is more of a red-orange color. Yeah. And so initially it'll go here and then eventually ends up here. So overall, after complete oxidation here of the pennies, we're going to go all the way to CuO solid. And so if we add up these two reactions here, the Cu2s cancel out. Not like, in a way like spectators, but in a way not like spectators, because it's a step on the way there. And so this is the overall, if we give it enough time. The same thing with carbon. You know, carbon is a variable charge. What's the maximum charge on carbon? Somebody took a here at a table. 4 plus, good. But it doesn't have to go to 4 plus. For example, if we oxidize carbon, it might form carbon monoxide, which is carbon plus 2. And so it might not go all the way. And so in this case, we'd have 1/2. Or, you know, it could be carbon, which is a solid. Carbon solid plus a full O2 gas. This will take us to CO2 gas. And so which is it? Do we form CO or do we form CO2? Which one it is depends on the conditions. Depends on condition. And so if I were to ask you this,
I just have a question with the previous one. Why doesn't it produce
well, it should be 2. Sorry. This one? Yeah, it should be 2. Yeah, it's got to be balanced. 2 coppers, 2 coppers, 2 oxygens, 2 oxygens. That's balanced. So, which one? Okay, can you tell me in theory which one's going to form? In theory, can you give me a theoretical prediction? You know, are you going to form 75% of this, 25% of that? Or is the theory kind of tough? It's kind of tough to predict. Obviously, if you're in an oxygen-starved environment, then you're going to form carbon monoxide, right? So you got to watch out. But tell me what is oxygen-starved, you know? At what point are we going to be starting to form a lot of carbon monoxide? At what point? And so theoretically, that's tough. So what do you think people do? You know, because in chemistry, there's a multiple-prong approach. What do you think chemists do when it's kind of tough theoretically? Do experiments. You know, they just try it and see what happens. Try it and see what happens. Try it and see what happens. That's it. And sometimes the theoretical predictions are not so easy. And so there's still a lot of experimental basis in chemical reactions, you know, to see what forms. And now we could have the reverse of this. Obviously, if you have oxidized pennies like this, how can you reverse this? You know, one thing what people do is they don't reverse it. You know what they do is if they want to clean their pennies, they'll scratch it with sandpaper. In fact, that's what you're supposed to do in this particular lab, I think. You're supposed to take the metals and then scratch off the oxide coating. If we're going to use lead, I don't want you to scratch the oxide coating off the lead. And so one thing is some people will scratch or polish their pennies which removes this, but we're going to be losing copper in the process. Another way that people can try to reverse this is they'll attack it with something. But you know, overall, we could try to just heat it up. If we heat this up, this is the symbol for heat, this delta, then it can revert back, you know, to 2 copper plus the O2 gas. Heating this up to high temperature.
When you heat it up, do you not lose any of the copper?
You won't lose any of the copper. You heat this up in an oxygen, even if it's an oxygen environment, it'll melt, you know, and you can't do everything like that. There are other ways. You could do this at room temperature. You could do this at room temperature or slightly above room temperature by using another agent. So for example, I've done this reaction myself where I use copper. I take the oxidized copper and then add hydrogen gas to it. If I add hydrogen gas, what do you think forms? Copper and water. So we get some, this requires a little bit of heat, but it's a little bit dangerous because hydrogen gas. And so this is an alternate way. You know, because if this is difficult, you might try this, might be easier to do. This is not an example of a element plus element. This is an alternate redox reaction here. We'll talk about. So this is an element plus element combination. Usually if it's fixed charged, it's easy to predict. If it's variable charged, it depends on the conditions what charge we get. Okay, the next type of reaction is single replacement. And so let's look at that quickly. The single replacement has the A plus BX or A plus BC forming. And so it's going to be A plus BX yields AX plus B. AX plus B. This is the single replacement form. And A is, this is what A is. Typically, A is an element. And then we have B, which is a compound. And so B is going to be some cation, you know, a B plus X. And then we're going to have X, which is an anion, you know, minus X, something like that. Or it could be some ratio. It doesn't have to be a 1-to-1. AX is going to be a compound now, here. And B is going to be the element here. And so the compound that forms, it's going to be A, you know, plus X, X minus X, something like that. The charges could vary depending on what we're forming. But essentially what we're going to do is we're going to take element A, which has a 0 charge, and then go to positive charge. If A goes from a 0 charge to positive charge, it loses electrons. If it loses electrons, we call it a reducing agent. A is a reducing agent. Reducing agents lose electrons. Reducing agent. If we look at B plus goes from a positive charge to a 0 charge in the element. And so B plus will be gaining electrons. This gains electrons. If something gains electrons, then B plus is called the oxidizing agent. So oxidizing agents take electrons, reducing agents give up electrons. So in other words, the oxidizing agent takes electrons from the reducing agent. The oxidizing agent oxidizes the reducing agent here. And so it takes time to get this vocabulary down. X is a spectator. Do you see X? Nothing happens to. So X is a spectator.
So the gained electrons is the oxidizing agent.
Yep. So what makes a good oxidizing agent? A good oxidizing agent really wants electrons. Well, what really wants electrons? Things with a high positive charge. The higher the positive charge, the more it wants electrons. There are other things that make a good oxidizing agent. The size and other factors. So it's not just charge alone that dictates it. But charge is an important factor nonetheless. So we're going to do, let's do this reaction here. Which is going to be, this is like magnesium again. So we'll take magnesium solid and then add some HCl, aqueous to it. If we take magnesium solid and HCl, then this follows the A plus BX pattern. You see it? A plus BX pattern. So what forms here? Okay, and, it's going to be magnesium chloride, but what's the formula for magnesium chloride? MgCl2. MgCl2. Okay, now there's water present. Is MgCl2, well, we'll look at that in a minute. But and then what else will form here? Yeah, the element hydrogen. The element hydrogen is diatomic, and so we have to make sure it's H2, not just H. And so what we say is this. Magnesium is the reducing agent. What's the oxidizing agent? The oxidizing agent is H+. H+. And so H+ has multiple chemical properties. One chemical property of H+ is it's what we call an acid. H+ is an acid, right? But H+ can also be a oxidizing agent. It's not a base, but it's an oxidizing agent. And so H+ is the oxidizing. What's chloride? What's chloride's role? Spectator. And so H+ oxidizes magnesium. In the process forms magnesium 2+ and hydrogen gas. That's how we read this. And you have to, it takes time to get the jargon down. And so you have to go through these over and over to get it. But let's go ahead and see if there's a driving force. Is there a driving force? Well, for single replacement, we use something called the activity series. And so what is the activity series? The activity series is in your supplement, and it's also in the book. And so let's take a look at the activity series here. Let me get this. You'll find this in reactions. Here. A bunch of So we go through, let's say, chemical reactions. This is a chem compact here. And we look for the activity series, which is on page 111. Oops, you can't see it, can you? Outlet. Here's my movement. We're wondering why they had the plug way over here. Outlet blew out. Okay. This isn't working either. I'll just write down the activity series. The activity series lists this. These are reducing agent strengths. Reducing agent strength. And it's listed from the top down. From the top is the strongest reducing agent. The strongest reducing agent just means that it, and these you don't have to memorize, but it just means that it's not so difficult to take the electron. And so one of the species that's the easiest to take the electrons from is lithium solid. And so this is the most active. In other words, this is what we call the strongest RA on the chart. There's stronger RAs than this. RA stands for, what do you think RA stands for? Reducing agent. Okay, then the other, when we look at it, there's going to be other group 1s. Other group 1s. So the group 1s are pretty good at losing their electrons, like sodium metal. You know, sodium metal is quite reactive. It's not number 1, but it's pretty reactive. Do you remember what happened to sodium metal in Lake
Yes.
Lenore, Washington? That goes to show it's pretty strong. And then we have group 2s. Then we have these are the patterns that I look at. Other, group 2s. It's not exactly in this order. You have to look because there's some group 2s that might be better than a group 1. And so there's some intermixing. But when we look at the overall pattern, actually, you should do this, and you'll see. Then we have others, like the transition metals. So other transition metals here. And then at the bottom of the list, we have the Nobel metals. The Nobel metals. And so let's just fill in some of these, like lithium. Lithium, and then we have sodium, and then down here we might have some iron. And that down here we'll have things like the least reactive would be like what? Silver. Francium's highly reactive. Francium's very dangerous. No, gold. What do you think is hardest to oxidize? Gold and platinum. And so these are going to be at the bottom of the list. Iron is a little easier. Sodium, lithium, those are very easy to oxidize. Very easy to oxidize because they lose their electrons so easily. And then we have something here that's going to be hydrogen. Is on this list. Hydrogen is also a reducer. It has electrons that it can give up, and so that's a list. Or I can show you another list here. I'll show you another list. Do you see this lithium solid? Memorize it. What do you know about lithium solid? Yeah, it's going to be the most powerful or the strongest what on the chart? It's going to be the strongest RA on the chart. What was RA again? Yeah, it's the strongest reducing agent. And so what we see here is we see an inverted activity series. What's the strongest RA? Lithium. And then the second strongest? Potassium. Followed by, let's just read them off. Calcium.
Sodium, magnesium, aluminum, zinc, iron,
Hydrogen. And then, what's that one?
Is that sulfuric?
Well, no, it's gas, so we wouldn't call it hydrosulfuric acid, we call it hydrogen sulfide, followed by tin 2, followed by, well, okay, that water is tricky because that's water plus, what do we call this? Sulfur dioxide. Iodide, yeah. Hydrogen peroxide.
Iron, silver,
Nitrogen monoxide in water, or nitric oxide, it's also called. Iodine in water. This is just water. This is water alone. So water actually can lose electrons. Water can, in other words, water can be a reducing agent. And then 2, chromium 3, chloride. Actually, the worst, what is the worst? What species does not want to lose electrons? What's the hardest to oxidize on this chart? What's the worst reducing agent? Not fluorine. It's called, F minus is not called fluorine. F minus is called fluoride. Fluoride is the absolute worst. It's the hardest to give up electrons. Well, if it's the hardest to give up electrons, then it wants that electron very badly. If it wants that electron very badly, then that means fluorine really wants electrons, because fluoride holds on to them. And so fluorine is what we call the most powerful OA. What do you think OA stands for? Oxidizing agent. And so you need to reference this. I don't even bother with the activity series if I have this chart, because it contains everything. And so remember the driving force for metathesis: stronger acid, weaker acid. And you might ask, what about the bases? Well, if you get the acids right, the bases must follow. When you're doing single replacement, they say if you get the reducing agents right, then the oxidizing agents must follow. You know? And so for single replacement, they only look at the reducing agent, the activity of the reducing agent. So what we want to do is we want to go from stronger reducing agent to weaker reducing agent. And so let's compare the two reducing agents, magnesium and hydrogen. Didn't we see those earlier on this chart? And so which one is a more powerful reducing agent? So let's take a look. Magnesium or hydrogen. And so these are all the reducing agents. Here's magnesium, here's hydrogen. Which one's more powerful? Magnesium. In the activity series in your book, it's going to be flipped upside down, because they're only looking at reducing agents. If they're only looking at reducing agents, then let's just put the strongest at the top. This chart is looking at both, because there's a conjugate relationship. You know, the conjugate relationship is if fluorine really wants electrons, then fluoride doesn't let them go. And so fluorine is a powerful oxidizer, fluoride is the weakest reducer on the chart. Okay, so what we have is, in the parlance of single replacement, we call this more active. More active just means a stronger Ra. And then this goes to less active. Less active means a weaker Ra. Here. Okay, so we have a driving force. There's a driving force present. If there's a driving force present, then we need to balance it. And so to balance it, we'll need two HCl's, and that's it. So for single replacement, we'll do a CE, and then we'll state the driving force, and then we'll do an IE. What's the IE for this? So magnesium solid, do we break that apart? No. No. If you accidentally drop some magnesium metal into water, will the water attack it? So we've got magnesium solid plus 2H plus. Water can break this apart. Plus 2Cl minus. This is going to produce MgCl2. Oops, no. Does MgCl2 stay together or break apart? Yeah, chlorides are soluble except for silver, lead, mercury. So it's going to break apart into Mg2 plus 2Cl minus plus H2. H2 doesn't get broken apart, it's a molecule.
So you don't write the charge to the molecule?
There's no charge on H2. It's an element, neutral. That's because H plus gained electrons. What happened to chloride? Chloride is a spectator. And so in the NIE, this is what we see. The NIE is going to show us Mg solid, our reducing agent, is oxidized by our oxidizing agent, 2H pluses. So the 2H pluses will attack the magnesium, strip the electrons off that, creating the magnesium 2 plus ions, and then each hydrogen will gain an electron. If each hydrogen gains an electron, then we form H2 gas, the element, hydrogen gas. And so here we have our reducing agent A, here we have our oxidizing agent B plus, here we have, in the reverse direction, this would be the oxidizing agent, this would be the reverse reducing agent in the reverse direction. So are there any questions about this here? So this is single replacement. The advantage of single replacement is it's easy. Advantage, easy. Disadvantage, it does not work always. Disadvantage. Fails for certain types of reactions. So what do you do? If it fails for certain types of reactions, what do you do? Well, what our book does is just not do those reactions. You know, if it's going to fail for this reaction, they're not going to put that reaction in the homework, and they're not going to put that reaction in the text, right? But, you know, is that appropriate thing? Because what happens is it'll give you the misconception that it works, and it should work. But if it fails, then it's not working. And so there are two instances where it fails. It fails, one, it fails for oxidizing acids. Oxidizing versus mineral acids. And so if we're looking at something like HX, in a mineral acid, H plus is the oxidizer. In an oxidizing acid, X minus is the oxidizer. And two, it fails when A is an oxidizer. Not a reducer. And so what we could do is we could memorize each of these exceptions, and then correct for it. Do you want to do that? No, because there are a lot of exceptions, and to memorize each one is too much. Right? And so if you're not dealing with an exception, then we're okay. Well, how do you know we're not dealing with an exception? Then we can use single replacement. Well, what we have to do is we have to familiarize ourselves with the chart. So the first thing is you look at the common reducers. You know, what do common reducers have in common? Most of the reducers are. Well, let's get more specific than that. Most of the reducers are. You could have solid dirt, solid grass, solid wood. Most of the reducers are solid metals. Yeah, most of the reducers are solid metals. Do you see that? But some of them aren't. Let's look at the oxidizers. What do the oxidizers have in common? And so let's read down the oxidizer list. This is the first step in, when you have a lot of data like this, first step is we take our observations and then we start to look for patterns and this kind of stuff. And so when we look at the oxidizers, let's read them off. What's this? Fluorine gas. Ozone gas. S2O8 2 minus, you're not responsible for. This is one of those ones that you don't have to worry about. But S2O8 2 minus has very interesting charge on that. What's the maximum charge on sulfur? What's the charge on sulfur here if we were to do this just straight charge? So this is -2 oxygen. -2 times 8 of them, we have -16. So this has got to be +14. And so that's +7. So this is kind of unusual looking at this. Do you see it's a little bit unusual? What's this one? H2O2. Hydrogen peroxide and in acid. We call it in acid. The H plus is acid. What's this one? Permanganate in acid. This one. Lead 2 oxide or lead 4 oxide?
No, lead 4.
Lead 4 oxide. Lead 4 oxide, this is the oxidizer in your car battery. In your car battery, you need an oxidizer. The oxidizer pulls electrons from the reducer. The reducer in your battery is lead metal. The oxidizer is lead 4 oxide. And what happens is the oxidizer pulls electrons off the lead and feeds them through your car radio or whatever else that needs electricity. Is
Why
that-
is it 4?
What's that?
Why is it 4?
Because each oxygen is -2. You have 2 of them, so -2 times 2 is -4. This has got to be +4. You only have 1 lead. What's this one? Chlorine gas. So the halogens, fluorine gas, chlorine gas, are good oxidizers. Bromine, good oxidizers. They're only 1 electron away from what they want. Oh, what's this one called? This is called dichromate. Good. You guys have been busy. The nomenclature, that's good. A lot of people still struggle with this all the way up to the test. And I'm glad. MnO2? Manganese? Is manganese fixed charge or variable charge? No, variable. Magnesium's fixed charge. Manganese is variable charge. Manganese 4 oxide. What's the charge on manganese up here? The manganese up here is plus. It's +7. The manganese down here is plus. Which one wants electrons more? +7 manganese or +4 manganese? +7, so it's going to be a more powerful oxidizer. Now, oxidizers take electrons, so a lot of people get confused. This already has extra electron. Do you see the negative charge? Why would something that has a negative charge, isn't there Coulombic repulsion? That is, isn't there electrostatic repulsion? It's negative. Why would it want more electrons? Well, it's because where does that negative go? That negative doesn't go on manganese. That negative goes on, actually, when we look at manganese, it's going to be manganese in the +7, and then we have 1, 2, 3, 4. 4 oxides. Oh, shoot. How much battery do I have? My battery is down. Okay, that negative charge is a result of these oxygens. Now, these oxygens are happy at -2. It's the manganese that's unhappy at +7. And so that excess negative charge is a result of all this. And so what we're looking at is, yes, even though that's negative charge, it wants electrons. How many electrons does it want? It wants 5 electrons. If it takes 5 electrons, what does it form? It goes from manganese +7 to manganese +2. You see that, how it works? Why do we need the H+? Can you tell me why we need the H+ there? We need the H+ because of the oxides. Are oxides happy alone? No. One thing you should know about oxides is oxides are extremely powerful. Extremely powerful. I didn't make you memorize the powerful bases. Is oxide one of the powerful bases? Yeah. Oxide is extremely powerful base. So we need this H+. In order, oxide alone is not stable, but oxide with hydrogen is stable, and it forms dihydrogen monoxide, which is water. And so we need the H+ to form water, which stabilizes. Now, these are the patterns you see. Each time we see H+, what's one of the products? Water. Water. Do you see that? And so there's definitely a lot of patterns in here. And we can see, not each time, because there's sometimes we see H+ and it just forms hydrogen gas. But let me tell you the difference between a oxidizing acid and a mineral acid. One of the most common oxidizing acids is nitric acid. And so let's do nitric versus HCl. If we do nitric versus HCl, nitric acid has nitrate. Nitrate, what's the positive charge on nitrogen and nitrate? +5. And it's +5 that's kind of high. In fact, that's the maximum positive charge on nitrogen. So that means that this really wants electron compared to H plus. When we look at H plus alone, it's a lot weaker. And so a mineral acid is like HCl. HCl consists of H plus and Cl minus. Does Cl minus want more electrons, or is Cl minus happy as is? Cl minus wants more electrons? It's happy as is, right? And therefore the oxidizer is just H plus, and chloride could just be a spectator. But if we look at nitric acid consists of H plus and nitrate. Which one wants electrons more, H plus or nitrate? Nitrate wants electrons more. And so do you think nitrate's going to be happy being a spectator? Nitrate is totally unhappy being a spectator, therefore single replacement fails. Single replacement is always going to fail if X is a more powerful oxidizer than B. So single replacement fails if X is a more powerful oxidizer than B. Single replacement also fails if A is a more powerful oxidizer than B. And so let me give you an example of that. Let's say we take chlorine and hydrogen iodide, or hydroiodic acid. And so if we take chlorine gas and hydroiodic acid, then if we do the single replacement, A is going to be the oxidizer, right? B is, well, A is not the oxidizer. A should be the reducer. B should be the oxidizer. But let's take a look. Here is H plus, the B. Where is chlorine? Where is chlorine? Do you see chlorine? Actually, that's chlorine. Where's H plus? Which one's a more powerful oxidizer? Chlorine. Therefore, single replacement fails because single replacement just assumes that everybody has their role. A has its role, B has its role, X has its role. If you change the players, the actors, then it's not going to fit always, you know? And so what our book does is it limits it. Our book is going to say, okay, these actors are not allowed in my play, right? But is that how nature works? No, that's not how nature works. And so I'm not going to spend much time with single replacement because there's a more powerful method that we can use than single replacement. What's a more powerful method? The more powerful method is the chart method. The chart method. But before we do the chart method, let me talk about combustion. Combustion follows a simple pattern. And so if we have CXHY, do you know what this is called? CXHY? It's called a hydrocarbon, like methane, CH4, like ethane, C2H6, etc. Hydrocarbons can burn in O2 gas. And do you know what happens when hydrocarbons burn? They form CO2 because the carbon gets oxidized, and then oxygen picks up electrons, forming the oxide, but we need the dihydrogen monoxide, which is H2O. And so we're going to form CO2 and water. We could take these CXHYs. We can also take CHYs, OZs. These are called carbohydrates, alcohols, ethers. There are a whole bunch of CHO compounds. These also burn, and they'll just form CO2 and water. And so hydrocarbons and other organics with carbon, hydrogen, and oxygen combust. So some of the best hydrocarbons would be like an alcohol. Let me just do one, and then we'll look at at the other chart method. And so if we look at an alcohol, let's take ethanol. Does ethanol burn?
Yes.
Yeah. Ethanol is given this formula, C2H5OH. And so what we're going to do is we're going to combine it and then look at the charge. We're going to call this C2H6O. All right, we look at this and we look at the typical charge. Carbon, variable charge typically, or fixed charge typically? It's variable charge, but we don't know the charge, right? But hydrogen, we know the charge. What's the charge on hydrogen? +1. Oxygen, we should know the charge. What's the charge on oxygen? -2. This will allow us to figure out the charge on carbon, because all these charges have to add up to 0. And so if I do +1 times 6, -2 times 1, and then we have x times 2. And when we sum up these charges, they have to equal to 0. So -2 times 1 is -2. +1 times 6 is +6. So +6 -2 plus what gives us 0? And so this is going to be +4, then this has got to be -2. -2. So the carbon is -2. Well, what does the charge range for carbon? Carbon varies from 4 to -4. And so this is in that range. And so what happens here is this is going to be a reducing agent. That is, it has electrons. It can give up, the carbon can give up electrons. And so we'll do +O2, and then we'll burn it. And that's going to form CO2 and water. So if we burn ethanol, we'll get CO2 and water. And then we got to balance it. We got 2 carbons here. We got 2 carbons there. We have 6 hydrogens here. We're going to get 3 waters here. And then we save O2 for last. And so on the right, we have 4 plus 3 is 7. 7 oxygens on the right. And then we have 1 plus x times 2. And so x times is going to be 3. 1, and so it's going to be 1 plus 6 gives us 7, and then 4 plus 3 gives us 7. So that's 7 and 7. And so ethanol is a liquid, O2 is a gas, CO2 is a gas. And so this is the combustion reaction here. Combustion of ethanol. All right, single replacement, I didn't bold that because we don't need that really. We could just use the chart method. The chart method is just like very similar to doing acid base, Bronsted acid base. So one, we got to get familiar with the chart. So let's just, getting familiar means reading this chart. I read it, when I'm learning a chart, something, it's not memorizing. You don't have to memorize it, but you read it a few times, just to get familiar with it, right? Because if you never look at the chart until the test, then you're going to have confusing things that arise. And so let's just go ahead and read it. Well, what's this one? Cr2O7 2- is dichromate. This is manganese 4 oxide. What's this? O2 is oxygen and H+. So what we say is these are the powerful oxidizers here. And so oxygen is a moderately powerful oxidizer in the presence of H+. What's this one? IO3 minus? Iodite? Iodate, yeah, good. Iodate. Br2? Br2 is a liquid. Cl2 is a gas. F2 is a gas. So bromine is a liquid, so red-orange liquid, and it is a moderate oxidizer. And it's called bromine. What's this one? Nitrate and acid. Well, nitrate and acid is called nitric acid. This is nitric acid. What's this? Silver ions. Silver ions actually want electrons. Silver ions are moderate oxidizer. They want electrons to form silver. So, well, it makes sense. Silver metal is stable. It's one of the coinage metals. This one? Iron 3 wants electrons, but it doesn't want 3 electrons. Iron 3 just wants 1 electron to form iron 2. And then we have, didn't we just see this? Didn't we just see oxygen? This is why you got to look at the charts beforehand. Because then you can say, okay, I know what's going on here. You tell me what's going on here. Why do we see oxygen repeat? And why is this oxygen more powerful than this oxygen?
Because there's 4 hydrogens.
Yeah, because there's 4 hydrogens and we form, whereas this oxygen, there's only 2 and we form hydrogen peroxide. And so even though it's the same reactant, the products are different. Which one's a more stable product, water or hydrogen peroxide? Water. And so therefore this one is more powerful. So if we have a choice of 2 oxygens, we're going to use a more powerful oxygen. Okay, then what do we have? I2. I2 is actually a solid. This is a purple solid. So iodine's a solid, bromine's a liquid, chlorine's a gas, fluorine's a gas. Those are the halogens. Iodine is going to be a lot less powerful of an oxidizer than fluorine, and that has to do with the size. Fluorine's very small, iodine's very big. And so fluorine's much more powerful. And then we have what? Copper 2. Copper 2 goes, it takes 2 electrons and goes all the way to copper metal. This does not stop at copper 1. In fact, when we look for copper metal, there's only one entry for copper metal, and that's this one. And so whenever we do copper metal in redox, we're always going to take it to copper 2. We aren't going to go to copper 1. We're going to take it to copper 2. Okay, what is this one? Sulfate in acid is called sulfuric acid, which is a mineral acid or an oxidizing acid? This is an oxidizing acid because sulfate is a more powerful oxidizer than H+. Whereas HCl, chloride, is chloride even? No, chloride's not even on here. And so we got sulfuric acid, then we have, well, why don't they call it sulfuric acid? They don't call it sulfuric acid because we could take sodium sulfate and HCl. If we take sodium sulfate and HCl, we're going to get the same thing. We're going to get sulfate ions and we're going to get hydrogen ions. Or we could take, what else? We could take magnesium sulfate and acetic acid to get the same kind of thing, the same kind of mixture. All right, then we have sulfur. Sulfur is a less powerful oxidizer than oxygen. And that has to do with size as well. And sulfur is a lot bigger, oxygen is a lot smaller, even though they're in the same family. And then we have H+. H+ is a moderate oxidizer. And then we have all these cations. What's the worst oxidizer on this chart? No, fluoride is the worst reducer on this chart. What's the worst oxidizer on this chart? Lithium. No, lithium is the strongest, most powerful reducer. Lithium is the most powerful. The worst oxidizer on this chart is, what do we call that? We don't call it lithium, we call it lithium ion. Lithium ion is the worst. Or is it the worst? Hey, doesn't this chart go down? Ah.
Oh, no.
No, shouldn't it be